is a dichroic block. Now that's a special type of prism which splits light just into its red, green and blue parts. But as it's right in the middle of the camera, you can't see it. So over here we've taken one out to have a look at.
Right, and here's the dichroic block, and it does look a bit like a prism. How does it work?
Well, here we have an ordinary white light source, okay? Now watch what happens when I put the block in front of that.
Ah, magic. Blue, green and red. You've split the light up into the three primary colours of light, haven't you? And presumably that's what happens with real pictures.
Yes.
So why don't we try pointing it at Jarton and see if it works?
Okay. Well, if you look through the block now, you should be able to see the red, green and blue pictures of him.
Right, now this one should be green. And there's a blue one. And round this side is the red Jarton. So now you've got three separate pictures. What happens to them?
Well, they're sent along 3 separate cables to the camera control room. So shall we go along and see what happens there if Jarton stays here in front of the cameras?
Suits me.
Right, well, here we have the controls for the cameras. And it's actually these knobs which change the amount of each of the 3 colours in the picture.
Well, can we have a look at the 3 colour pictures separately then?
Sure. If we look at Jarton, there's the blue picture. There's the red one. And there's the green. Now, of course, for a full picture, we do need all 3. So if we go back to the blue, add the red,
Not much difference there, really.
and finally mix in the last one, the green.
Goodness me, what difference the green makes. Yes, well then of course you've got the problem, I suppose, of getting the exact amount of each different colour to make the picture look normal, haven't you?
That's right, and it's not just for the one camera. We've got 4 cameras in the studio, and Jarton must look the same on each of them. Now, this camera looks reasonably good. That one's good as well. That's the one we were playing with a minute ago, so it's slightly off. But that one is well off.
You don't look very well, Jarton.
Now, that's not the only problem we have. It's very important that all 3 pictures, the red, the green and the blue ones, sit exactly on top of each other. If they don't, then this is the sort of effect that we get. That's moving the red out. And if we move the blue out,
Yes, colourful, but a bit weird.
and when I stick them back again, wind the blue back in, and the red, now that's what the camera should look like.
Shame. I think I preferred the weird version. OK, so the colour pictures are transmitted to the TV set, but how do they get onto the screen, Rod?
Well, your television takes the 3 separate colour signals, and these go to 3 electron guns at the back of your TV, and they then fire their own signals towards the front of the screen. It's easier to see on this model. Now, here we have the 3 electron guns at the back, one for the red signal, one for the green signal, and one for the blue signal. And they then fire their own signals towards the front of the screen.
So what's this for here?
Right, well, near the front of the tube, the signals go through a mesh. It's called a shadow mask, and it's a bit like a fine sieve. It makes sure that the signals from the guns arrive at the right dots. Now, the dots are arranged in groups of 3, and the whole screen's covered in them.
So on a real television screen, how many would there be about?
It's about 1.5 million.
Goodness.
If you look closely, you could actually see the dots on your screen. On some televisions, they're more of a square shape.
You might see them more easily if you hold a glass of water up to the screen, because that will magnify them.
We've got a special close-up camera rig, so you can see what happens when there's different colour on the screen.
If the screen's all white, the red, green and blue dots should all be equally bright. Yes, they are.
And here's red, green and blue. It's what you'd expect, really. But what about yellow? That the blue dots went off and the red and green ones came on. And here's magenta and cyan.
And if we look at the ordinary picture of the studio, instead of pure colour, you can see that the dots change in brightness as we move and the picture changes. And even when you know it's only made up of red, green and blue dots, it still looks pretty convincing. These these are some of the beautiful colours you can get when you dye wools the natural way, using plants. And in fact, they make up into just beautiful clothes as well. I've come here today to meet somebody who specialises in vegetable dyes. Her name's Ray Napier. Hello, Ray.
Hello.
Well, these are some of the things you use for your vegetable dyes, but they don't look like vegetables to me.
They're mainly trees. Because I dye all the year round, I can't really use seasonal things.
But some of these things are plants from the garden, aren't they?
Yes, this is world, which I grow in the garden. Persian berries and fustic, which is a tropical plant, all of which give yellows.
Yes.
The rest of them are really woods. This is yew, which gives oranges, Brazil wood, which gives reddy colours, Sanders wood, and logwood.
Yes, now that logwood, you wouldn't expect to get blue from that one, would you?
No, not really.
Those ones look interesting. What are they?
These are roots. This is galanga and madder, which gives an orangey colour. And this one, what do you think this is?
I don't know. Could they be seeds of some sort?
It's cochineal. It's actually a beetle.
Oh, yes.
They're cochineal. It gives reds and lovely pinks.
Oh, a bit like...
Yes, that's cochineal, and this one is actually logwood.
Yes, beautiful. Now, what are these used for?
These are mineral salts. They're mordants. There's alum, tin, chrome, copper sulfate, and ferrous sulfate. They help the wool to take up the colour. You'll see later what different sorts of colours you get by using different mordants.
Right, so using the mordants is the very first thing you have
Yes.
to do. So shall we go and see how you do that then?
Sure.
So, Ray, this is how the wool starts out, isn't it?
Yes, this is white wool, about 100 grams.
Yes. And what mordant are you going to put with it?
This is alum, so we use about a quarter of the weight of wool, which we make into a solution, and then add to a larger quantity of water.
So that the wool has freedom to move and then it isn't all patchy. Right.
Stir it round.
I put that
Okay.
in. Right.
That should be warm and wetted.
Lovely. Now, that goes on to...
Onto the stove to heat for about 3/4 of an hour to an hour.
Right. And when it comes off the stove, it'll look a bit
This is
like...
the alum.
Yes, that's the
Whereas
alum.
Using other mordants, this would be copper sulfate, that's chrome, and that one is tin.
Not much difference between them at the moment.
Not at this stage, but later on when we look at the dye pots, you'll see a difference there.
Right. Shall we go and have a look at the dye being prepared then?
Fine.
And so this is the dye we're using.
Yes, that's Brazil wood,
Yes.
which we put about the same quantity as weight of wool you're going to dye into the dye pot and boil it up for at least an hour.
And you can see, in fact, the colour has changed quite drastically.
Yes,
hasn't it?
quite a lot.
It's gone to
And you
beautiful,
get
rich
this
red.
lovely, rich red liquid.
Beautiful crimson colour. But you don't put the wool into this pan, do you?
No, I strain it into the larger dye pot with a lot more water so that the wool has room to move around.
So this is the dye bath full of Brazil wood dye.
Yes, and this is the wool that we have already mordanted that we add to the dye bath.
And in fact, already, you've got a bit of the colour, haven't you?
Yes, but if you leave it in for at least half an hour, you'll see a much better colour range.
Right, so we'll leave it there to cook for about half an hour.
Now these are some that have been in overnight.
Yes, they're much darker, they're beautiful.
Yes, and much wider range. You see the range of colours.
And that comes from the different mordants then, doesn't
Yes,
it?
you can tell from my code system of knots. I know by the number of knots which mordant I've used.
And that one is...
That one's alum, tin, chrome,
Yes,
copper sulfate,
yes.
ferrous sulfate.
And this one's actually quite different.
That one has got no mordant in it at all.
Yes.
But you see how uneven it's likely to come out.
Yes, and so that means it won't last as long, it'll actually fade.
It's
that
more
one, won't it?
likely to lose its colour, yes.
So Brazil wood gives you various shades of reddish purple.
Yes.
But do you have any other colours?
Yes, we have, for instance, some onion skins here,
Yes.
which you saw, and that is this range of colours.
An amazing range of colours there. Gold, brown. Beautiful, that is. And onion skins are one of the things you can use if you want to have a go at vegetable dyeing yourself. There are plenty of things around the house and garden you could use. Broccoli, wood, tea, beetroot, spices, or even marigolds or tomato plants, but that's the leaves and not the fruits. You can try almost anything as long as it's not a rare wild plant. You'll find that most plants will give you yellowy greens, but try avocado skins and surprisingly you could get a pinky colour if you boil the skins for long enough. You might also be surprised at what you get from red cabbage as well. If you're having a go at home rather than in the lab, do keep the dyes and the mordants away from food and don't use your best saucepans. Apart from wool, nylon gives results with quite a few vegetable dyes. Start with small samples first. Half the fun of vegetable dyeing is just trying things out, seeing what you can get. I can't guarantee, of course, that you'll get colours as lovely as the one that Ray dyes, but just remember, any colour except white is a success.
What colours do you reckon I'm wearing? But what about now? It's tricky, isn't it? It's a lot easier, though, in white light. My red cap and trousers reflect red light, and my green jacket reflects green light. And because white light contains all the colours of the rainbow, or spectrum, all the clothes I'm wearing can reflect their true colours. Now, if we change back to red light, my cap's okay, but look what happens to it under the green. There. Now you see if you can work out why. And what would blue light do to the rest of the colours I'm wearing? This is my little chum Fred. Hello, Fred. Fred's part of a theatrical mime show. And in fact, in a theatre, you can get lots of different special effects. All you want is different coloured spotlights, interesting costumes, and a well-designed set. Now, this is the model of a set built by 4 theatre design students called Carl, Emma, Lorna and Nonnie. So how do you go about choosing the colours for the production, then?
Well, first of all, we talked to the mime company, and they set us a brief, which was that they wanted warm and human colours, which is basically this red range here. But we tried out others to see what they'd look like, and here there's a cool green and blue here with the warmer colours. But we decided on a compromise, which was this, between the two.
Yeah, but aren't the colours and the lights going to change all that?
It's quite important to think about these quite a lot, because you can see that if I go like that, it washes out the reds completely, and all the blues become black or purple. So you have to think about it a lot.
Right, well, you've decided on the colours. How did you design the costumes?
Well, we sketched some ideas of the costumes, and then we chose some samples of material that we wanted to use. We had to choose fabric which would dye easily. We've got some here that the colours, and we ended up by dyeing white fabric a reddish colour.
And what's that other fabric?
That's a sample of the material from the set that's actually been painted, and we had to think about how they'd go together.
Well, as you can see in the model, the main part of the set is that silk tent, which has been painted different colours in order to pick up the different lights and create different moods in that way.
And why did you choose black for the floor cloth?
Well, the real colour of the theatre floor is a very strong wooden colour, and that would just kill off all the warm colours in the costume and the tent.
Of course, no show would be complete without its performers. And here's baby Fred again, being held by Mother Martina. Hello. Now, they're being bathed in a warm pink light, and that gives a sort of caring, motherly sort of feeling. Much more than you get from this character, who's Fred when he's grown up a bit. All right, Fred, settle down. Fred here has been worked by this lady behind, who is Anya. Look, see, a real person. But she wears all this black gear because in theatre there's a convention, anything black is invisible. And to all intents and purposes, Anya in this costume against the black background is invisible. The rest of the cast are wearing warm colours. But have a look at how those colours change with the lights in the party scene. Come on! Come on! Come on! Come on!
Everything should combine to make a final effect. A certain mood needs to be created for each scene, so everything works together, the lights, the costume, the sets, and also the music, which I wrote especially for the show.
The colour wheel works really well because the light reflected on the tent really adds to the movement, and so it becomes very, very fluid.
Wanna have a video with Blue Screen? Wanna have a video with Blue Screen? Wanna have a video with...
The white of the tent is quite like a blank canvas that we can paint any colour of light on it and give a different effect.
And that jelly provides food for them to grow on.
Oh.
And I'm also going to swab them with this cotton swab.
That's yet again another method that you're using there.
That's right.
I suppose it acts as a double check then, using two methods.
Quite.
Liz finished off sampling the sink with another contact plate and a quick swab of the taps. After that, she went round the rest of the kitchen, sampling the smooth worktop, the greasy table, the chopping board, the breadboard, and the drying up towel.
You're even doing the fridge. You don't find bacteria in there as well, do you?
Yes, bacteria grow in the fridge too. Cold just makes them grow more slowly.
Liz did a pretty thorough job in the kitchen, but that's only half the story. Next, the samples have to be grown in the lab. The swabs were streaked onto plates of agar jelly, which comes in two different colours. The white jelly provides food for most types of bacteria. The red jelly is best for growing bacteria from the human gut. The contact plates don't need anything more doing to them, and when all the other samples were done, they were all placed in a warm incubator. It's kept at 37 degrees Celsius, about human body temperature, which suits the bacteria really well. So they're left to grow overnight. Next day, when she got the results, I asked Liz to tell us what she'd found.
Right. Well, as we find in lots of kitchen sinks, a lot of bacteria growing on the kitchen sink. This is a moist sink area. A lot of food and rubbish goes down the sink, and you have a lot of bacteria growing. So many you can't even see individual bacteria. When I put the streak plate up here, you still can't even see any individual bacteria growing. So many growing there. I was quite surprised to find there are not as many bacteria growing in the U-tube as we do find. That may have been because a lot of water got flushed down in the morning with cleaning up and so on, and they got diluted. The tap, although I do expect to find bacteria contaminating the tap area, which is a sort of hand contact area, you get, I think there's more bacteria on this tap than would normally expect to find. But the whole sink area was so heavily contaminated that I expect they've got transferred to the tap as well in that way.
And what about the cleaning cloths?
Well, the dishcloth is nearly always the worst. And again, this dishcloth, you can't even see any individual bacteria, so many growing there. The dishcloth is a nice, moist, warm place with lots of bits of food particles in it, and the bacteria really love that area. But it's quite interesting to compare that with a dry cloth. For instance, the drying up cloth itself, very few bacteria growing on that. They don't grow in dry areas very well.
And the same was true of the smooth, dry worktop. Very few bacteria there. But the rough breadboard produced all these. They live on the food and grease trapped in the cracks of the wood. And the chopping board had lots of cuts and scratches, and bacteria. Even the fridge had quite a few bacteria, slowed down, but not killed by the cold. If you use a dye to stain the bacteria, they show up better under the microscope. This one magnifies them 100 times. Staining also helps sort them out into their different types. And live bacteria are even more amazing. And those bacteria multiply pretty fast. In fact, in 15 hours, one single bacterium can produce 1 million more. But don't panic. We've got Liz Scott again with us here today, and Liz also does research work into the best ways of cleaning up the bacteria. Now, we've got quite a few household cleaners here. There's all sorts. So which would you say is the best, Liz?
Well, we can use detergents to actually remove the grease and dirt that we can see.
Yeah, that's washing up liquid, soap powder, detergents, yeah.
That's right. But to kill bacteria properly, we need to use a disinfectant. There's quite a wide range of disinfectants, and some really are just a nice smell. But to do a good job, you need to use sodium hypochlorite, the ones we know as common household bleach.
Which is this selection of things here, isn't it?
That's right.
So how do you know those are the best, Liz?
Well, just as you saw me sampling surfaces in the home, we can do a similar thing for testing disinfectants.
Yeah.
And if you look at these 3 agar plates here, here's a surface before we treated it with anything at all, lots of bacteria growing on it. And here's a surface after we've wiped it down with detergent. Still a lot of bacteria on that plate. And then there's a surface that we've wiped down with sodium hypochlorite. No bacteria at all.
That's killed them all off, the detergent.
That's right.
Yeah, as you said. So it really works. What do we use bleach on a surface then, Liz?
Well, for sinks, drains and loos, we can use it neat from the bottle.
Yeah.
But for actually on a work surface, you have to dilute it with water. And as they all vary in strength, and we need to follow the instructions on the label for that.
Yeah, they've all got quite a lot of instructions too, so make a note of that. Look, Liz, if detergents get rid of the grease and the dirt that the bacteria live on, but bleach kills them completely, why not just mix them both together?
Well, you can actually buy thickened bleaches that have a detergent in them and remove the grease and kill the bacteria in one go. But it's not a good idea to mix our own cleaning chemicals at home, because for a start you might just stop the disinfectant working. And also it could be a dangerous thing to do.
Oh, I'll leave that then. Listen, Liz, will we ever get rid of bacteria completely?
No, we won't. But at least we can stop them growing too much and in the wrong places.
It's a relief anyway. Liz, thanks a lot.
We're all covered in skin, nearly 2 square metres of it, and that's a lot to keep clean, especially when you realise that it contains 3 million sweat glands, and that can make a litre of sweat a day, or even that much in an hour if it's very hot, or if you're very active. So it's not surprising that a lot of research is done into deodorants and antiperspirants. Dr. Malcolm Kennelly is from the Boots Consumer Products Research Lab. What's the problem with sweat, Malcolm?
Well, there's no problem with fresh sweat. It smells quite sweet. But as soon as the bacteria on the skin start to break it down, then it begins to smell.
And one of the smelliest places is under the armpits, isn't
That's
it?
right.
In fact, take a look at this T-shirt. You can see lots of skin bacteria, but they are worst under the arms.
Yes, we need to get rid of the bacteria under the armpits, and we use a deodorant or an antiperspirant to do this.
How can you check that the deodorant is doing its job?
Well, we use an agar plate here, which contains bacteria, and we place a drop of deodorant in the center here, incubate the plate for 24 hours, and that's the result.
Right, yes, there's quite a lot of bacteria growing around the outside here, but not at all much here in the middle, is there?
Yes, this clear zone is where the deodorant has stopped the bacteria from multiplying. This is called a zone of inhibition test.
Now, deodorants are not the same as antiperspirants, are they?
No, both will stop you smelling, but the antiperspirant will cut down how much you sweat.
And Malcolm's lab also uses a sweat test to see how well antiperspirants work. So if you want to have a go yourself, you can use this test to measure the amount of sweat you make during 10 minutes of exercise. Well, what have we got to do to start?
Well, first of all, we need an exercise bike and a volunteer.
I know the man. Charlton,
Go on, just this once then.
how are we going to measure his sweat?
Well, we're going to weigh it, and we're going to use these pads to soak up the sweat.
You've got them in boxes.
Well, that's to stop the sweat evaporating once we've collected it from Jarton.
Right, okay. You weigh, I'll note it down. That's the left.
Left weighs 58.88 grams.
58.88.
And the right weighs 60.69 grams.
60.69. Now that's before.
That's right.
Dry. Now he puts them on, does he?
Oh, right.
Is that okay now?
Yeah.
Right.
Yeah, I think so. Yeah, right. Okay. So, Malcolm, it's what, 10 minutes exercise on this thing, then I can stop, can I?
Yes, and 10 minutes rest to mop up any more sweat, and then we'll weigh the pads again.
Yeah, well, I'm going to need 10 minutes rest, I think. Right, let's go. Well, that's 10 minutes up now. So now for 10, whoops. Now for 10 minutes rest. Oh, I'm all wobbly. Yeah. Well, that's my 10 minutes rest. Now for some results.
Right, let's have the left one first.
Thank you. Thank you.
So you're going to weigh the left one first, aren't you?
We will, yes. The left one weighs 60.22 grams.
60.22 grams.
And the right one weighs 62.12 grams.
62.12 grams. Right. The left arm pad and box now weigh 60.22 grams. They started off weighing 58.88 grams. So, we do some subtraction there. 60.22 grams minus 58.88 grams, giving an answer of 1.34 grams for the amount of sweat from under your left armpit, Jarton.
Good.
Now, let's try the right one. The right arm pad and its box now weigh 62.12 grams. Before, they weighed 60.69 grams. So, let's do that on the calculator. 62.12 grams minus 60.69 grams equals 1.43 grams. So it's 1.43 grams of sweat from the right armpit. So why are we testing both armpits, Malcolm?
Well, when we test antiperspirants, we only treat one armpit, then we can compare it to the untreated one.
I see, and presumably when you've put antiperspirant under an armpit, that one hardly sweats at all.
Well, no, antiperspirants don't stop you sweating completely. It should cut down sweat by about a third. That's the sort of result I'd get in my lab, using a group of people under controlled conditions.
So, if you want to have a go yourself, do a sweat test, first without the antiperspirant, and then put the antiperspirant on just one armpit. Give it an hour or so to start working, and then do the test again. You can compare the two results to see how they've changed. And it's interesting to try out different types of antiperspirant as well. Try doing the sweat test with different sorts of exercise. Find out which one is the sweatiest.
When it comes to food, it's vital everything's kept very clean. Now, we're all eating more and more meals away from home in canteens, cafes and restaurants. And it's one of the jobs of the environmental health officer to make sure they come up to certain standards.
Mr. Faulty.
Hello.
These premises do not come up to the standard required by this authority. Specifically, lack of proper cleaning routines, dirty and greasy filters, greasy and encrusted deep fat fryer, dirty cracked and stained food preparation surfaces, dirty cracked and missing wall and floor tiles, dirty marked and stained utensils, dirty and greasy interior surfaces of the ventilator hoods.
Yes, about the deep fat fryer.
Inadequate temperature control and storage of dangerous foodstuffs, storage of cooked and raw meat in same trays, storage of raw meat above confection range.